Okay, here we go. Today is Tuesday, May 1st. Today we checked in our homework, which was identifying acids and base pairs. We went through that. Work key should be on my blog. All right. We grabbed a lab, which is the acid-base indicator lab, which we're planning on doing on Wednesday. Notes today are including, well, we're actually going to do them in the reverse order here. We're going to start here. We're going to do this, and then we're going to do this. So we're going to start by talking about the self-ionization constant of water. We're going to move to the hydronium ion concentration calculations, and then to the pH calculations. Today's homework, that is not the correct title. The title is Calculating pH, pOH, and then hydronium and hydroxide ion concentrations. Okay. What we're starting with today is where we left off. Kind of on yesterday. We talked about the fact that if you have water, it is going to spontaneously ionize into hydronium ions and into hydroxide ions. What does that mean? Well, that means that when we try and write a KEQ, we don't get to write the water because it's a liquid. We only get to write the hydronium and the hydroxide ions. Okay. This is a special KEQ. It's a special constant of equilibrium. We call it the self-ionization constant of water, or Kw. So we write it this way. Kw is hydronium ion concentration times hydroxide ion concentration. Now, if you notice this in the balanced equation here, we've got a 1-to-1 ratio for hydronium to hydroxide. So these two values are the exact same values. They don't cancel each other out. It's the same value. If you measure this at normal room temperatures, you find out that the concentration of hydronium ion is 1 times 10 to the negative 7. And the molarity, the concentration of the hydroxide ion concentration is the exact same thing. When you multiply these two things by each other, you get 1 times 10 to the negative 14, which this value is extremely important because anytime you're using a solution that uses water, you're always going to have these two numbers have a product of 1 times 10 to the negative 14th. This means we can actually do some math. Another interesting thing here, when we take up and we make up a solution of hydrochloric acid, it actually has hydroxide ions in it. You might not think that. You might think, okay, Mr. Kane, this is an acid, which means that what ion is it going to have in it? Well, it's going to have hydronium ion in it. But you know what? Yes, it's an acid, and that acid produces hydronium ion, but hey, check this out. It's a solution. It's a solution means that there's water in it. Water in it means that the H2O is automatically going to self-ionize into hydronium ion. And, oh yeah, there you go. It's got to form hydroxide ion also. So this solution of acid is going to have hydronium and hydroxide in it. Okay? How am I going to solve for how much hydroxide is there? Well, the Kw is simple. We've done this before. Well, we haven't done this before. We've seen this before on the last slide. The Kw of water is hydronium ion concentration times hydroxide ion concentration. Kw value never changes. The product of, let me see, I wrote this wrong. The product of hydronium times hydroxide should give you 1.00 times 10 to the negative 14th every single time. So if I'm looking for hydroxide ion concentration, I must know the hydronium ion concentration. This is a strong acid. It completely ionizes, which means that the amount of acid is also the amount of the concentration of the hydronium ion. Okay, we do a little math. We do a little algebra. 3.00 times 10 to the negative 5th. We divide by 3.00 times 10 to the negative 5th. This cancels, and we find out that the hydroxide ion concentration is 3.33 times 10 to the negative 10th. Does this make sense? Well, hydronium ion concentration, H3O plus, is a fairly large number, 10 to the negative 5th, compared to the smaller number for the base. This is an acid solution, so I should have a lot more acid component, hydronium ion, than I do hydroxide. And that's true. All right. Skipping the let's try these. Okay, if you find that useful, you can leave it up there and you can check it out. Press pause, and you can try those out. Okay. Useful information here. if one of the concentrations is higher, then the other one has to be smaller. All right, remember Kw is hydronium times hydroxide. So basically, if this number is large, that number has to be small. If this number is large, that means I've got more acid. Okay. If the hydroxide ion concentration on the other hand is large, then that must mean the hydronium is small. If the hydroxide is large, then we've got a base. As a matter of fact, that's exactly what this information right here says, and you're going to need to understand this. If I have a large amount, well, let me start this. The whole reason why I've got the center here, comparing hydronium to hydroxide, is because this is right in the middle, times 10 to the negative 14th. Half of that is times 10 to the negative 7th. All right? If more than half of it is hydronium, you got an acid. Or another way of looking at it, if half of it represents more than what's hydroxide, the basic part, then you've got an acid also, because you don't have enough base to make up more than half. All right? If the hydronium ion concentration, on the other hand, is equal to times 10 to the negative 7th, then the hydroxide has to be equal to it, and that means you've got a neutral solution. All right? If the hydronium ion concentration is less than half, now the other, what the half is plus then some, is made up of hydroxide. So that means you got a basic solution. Another way to look at that, if half is less than what is basic, then you got a basic solution. All right. Now, if you're thinking this is a bit heady and it's a bit difficult to think of because of these exponents that are here, you're right. Other people have thought about that too. You're still going to be responsible for being able to tell me if, based on concentrations, whether something's acidic, basic, or neutral. But somebody came along and figured out that that was difficult. All right, because we don't say on commercials, well, we do say on commercials, pH balanced for her, right? They don't say hydronium ion concentration balanced. So what happens is this. This guy, Sorensen, figures out in 1909 with his intense intelligence that hydronium ion and hydroxide ion concentrations have negative exponents, and they're kind of awkward. He doesn't like dealing with them. So he develops a scale to deal with that. He creates what's called the pH scale, which everybody knows about, to make it easier to understand. He calls it the pH scale because it stands for the power of hydrogen. That is literally what it stands for. It's not made up. I'm not making this stuff up. Now, I like to talk about hydronium rather than hydrogen because hydronium and hydrogen are basically the same thing. Bronsted-Lowry said that hydrogen was the acid component, and Arrhenius said the hydronium ion was it. Either way you look at it, we're still talking about what the acidic component is. Okay. Now, the way that he makes this easier is he bases his stuff with the pH scale on logarithmic math. And we're going to have to get into talking about what logarithmic math is. We won't get into it like your Algebra 2 teacher did. We're going to keep it in the natural log realm. But I'll tell you everything you need to know in the next 7.5 minutes or so. All right, calculating pH. How do we calculate a pH of something? Here it is. In order to find out what the pH is, you take the negative log of the hydronium ion concentration. It's that simple. So if you've got your calculator, let's try out this. The acid that we worked with in the first problem today had a hydronium ion concentration of 3.00 times 10. Let's see, I've got to look back and see what it said. It's 3 times 10 to the negative 5th. Okay. That was the molarity of the hydrochloric acid we used in that first problem. If you want to figure out what the pH of it is, we take the negative log of 3.00 times 10 to the negative 5th. It's that simple. Punch that into your calculator. My calculator, I punched the negative button first, then the log button, then 3.00 EE, negative 5th, in the parenthesis, and I get an answer of 4.52. pH is equal to 4.52. Now, I could teach you a new sig fig rule, but it's a lot easier just to tell you that every single pH that you come up with is going to have 2 digits past the decimal. If you don't have 2 digits past the decimal, it's not a pH value. Okay. Let's see. Some calculators require that you type this number first, then type log, then type the negative. So figure out what your calculator requires you to do. If you get 4.52, you're golden. Okay. something to talk about here, something to continue talking about here is that we can play around with this a little bit. Let me show you. I know that a hydronium ion concentration of 1.00 times 10 to the negative 7 is going to give me a neutral solution. Okay? If I take the negative log of 1.00 times 10 to the negative 7th, I find out that I get a pH of 7.00. That's kind of handy, isn't it? Look at that. I don't need any math. The exponent turned into the pH. If you don't believe me, check the calculation. Okay? If I have a hydronium ion concentration of 1 times 10 to the negative 5th, this is a larger number than that. So I'm expecting this to be an acid. Okay? Turns out that the pH, according to the calculator, is 5.00. If I go to extreme, 1 times 10 to the first, I'm still expecting that to be an acid. And I'm expecting it to be an acid because this number is larger than this number. I'm going to get a value of 1.00. So this is neutral. All of this, all the way up to 7.00 is acidic. So if you can memorize that 1 to 6.99 is acidic, you're golden for pH values. Okay, these are pHs. Neutral is 7.00. Now if we play with some numbers again, 1.00 times 10 to the negative 9, we get a base. Okay, you do the math, you get a pH of 9.00. You go to the other extreme, 1.00 times 10 to the negative 14. That's still a base. Reasoning, this is smaller than times 10 to the negative 7th. All right, so we get a pH of 14.0. It's not 3 digits, it's 2 digits past the decimal, so 14.00. Okay, these values are all basic. Okay, so 7.01 all the way to 14 are basic. 1.0 through 6.99 are acidic, and anything in the middle is neutral. All right, now let's check this out. There's something more that we need to get into. This logarithmic math has some meaning. A pH of 7.00 we talked about is neutral. Here's the question I want you to think about. Between these two pHs, which one is more acidic? Okay. This one is obviously more acidic because it has a pH that's lower. pHs of 1 through 7 are acidic, 1 being the most acidic. All right. Now the question is, what's the meaning here? The question I like to ask is, how many more times acidic is 5 than 7? A lot of people say it's 2. That's not what logarithmic math tells you. Logarithmic math is based on factors of 10. So each number, each value of one pH is a factor of 10 times more acidic. So 6 is 10 times more acidic than 7, and 5 is 10 times more acidic than 6. What that means when I take these two things together is that when I talk about the difference between the pH 5 to 7, that's a difference of 2, right? So that's 10 times 10 is the difference, so it's 100 times more acidic. Or as I like to say, because it's 2, it's 2 zeros after a 1. Okay? If you want to take this to an extreme, what's the difference in pH between 7 and 1? Okay, pH 7 to 1. How many times more acidic is 1 than 7? Well, that's a difference of 6 pH units. 6 pH units means that you're taking a multiple of 10 6 times. So it's 10 times 10 times 10 times 10 times 10 times 10. All right, what is that? Well, like I said, it's 6 zeros. So it's 1 million times more acidic to go from 7 to 1. Okay. The other important thing from this slide is right here. This is the rearranged equation. pH is equal to negative log of hydronium ion. If you want to solve for hydronium ion, though, you have to take 10 to the power of the negative pH. Okay. So what that means is that if I want to find out the hydronium ion concentration, H3O plus of a pH of, let's say 7. Well, I already know the answer to that. I don't have to do the math, but you can do the math in your calculator. 10 to the power of -7, you should get a hydronium ion concentration of 1.00 times 10 to the -7th. Okay. Now, for the purpose of checking to see that you've got these things right in your calculator, do a pH. You've got a pH of 2.37. Figure out what the hydronium ion concentration is. Hydronium ion concentration should be calculated as the 10 to the -2.37 power. Okay. You do that math, you should get 4.27 times 10 to the -3rd. All right. If you try a hydronium ion concentration of 12.0 times 10 to the -12, well, let's see. If I want the pH, pH is the negative log of 12.0 times 10 to the -12. If you plug that into your calculator correctly, you should get 10.92. I've got 2 more problems for you to try out and make sure you're getting things right. If you get all 4 of these right in your calculator, you should be doing just fine. If you don't get these right, then you're doing something wrong in your calculator. Figure it out. Okay. Just for interest's sake, this chart is usually in the textbook, so you can find it in there. Extremely acidic, 1 molar solution is pH 0. Other extreme, pH 14, sodium hydroxide, also known as lye, is an extreme base. In between, you've got pure water. Press pause and take a read if you like, but that's the basics, right? Last thing to talk about today, all right? POH and concentration of hydroxide. It turns out these things are the same idea as pH, only POH talks about the power of hydroxide. So you use the same calculation, only use hydroxide in place of the hydronium ion. All right, the concentration of hydroxide is calculated the same way when you use hydronium ion, hydroxide instead of hydronium ion. All right. Here's the other thing, guys. This is great for people who like to use their frontal lobes. pH plus POH always has to equal 14. So that means if you got a pH of 12.00 and you want to know what the POH is, do the math. What plus 12 equals 14? Yep, 2.00. All right, that should be it for today. Please make sure to do the worksheet, calculating pH, POH, hydronium, and hydroxide ion concentrations.